trying to show that account memory is actually that's 10 years ago. But on the LM geometry, they actually managed to reproduce the corresponding alpha correction. So without, basically they consider different droplet configuration. The superstar is the one I think right there. Right. That is a white spot right in the middle of the droplet.
Great.
Right. And I think they managed to come up with some other droplet configuration to fit what you were trying to say just now. This is the same phase space.
Okay.
And then they show that from this particular droplet picture, then they calculate geometry. Then I think they managed to show that this is a solution to the alpha prime corrected supergravity equation function.
Okay.
So that, I guess I mean that's
Yeah. I'd like to hear about it.
yeah, okay.
Okay, maybe I should move on. Any more comments? Okay. Good. So, second example. Now, learning mature geometries. So these are before the LLM geometries, and this is now about two branes, two stacks of branes. You have N1D brane, D1 brane, and N5 D5 branes, and here you have now A2 symmetries. The charge is preserved, and there's some similar picture. So you have now ADS3 cross S3 supergravity, and you consider two charge. So this is a two-charge system because you have two different branes, and you consider the black hole in this system, which is again a singular horizon, zero horizon black hole, but let me call it a black hole for this part. And this is supposed to be described by some two-dimensional CFT in the 1/2 BPS sector, and this half BPS sector is known to be described by free bosons. So it's like the X CFT on a free string. So you have some expansion of this X in terms of some oscillators labeled by N. So the state of these free bosons are described by some integers. So N1 corresponds to the number of excitations of the first level, and N2 is the excitation number of level 2, and so on and so forth. And there's some constraint. But anyway, you have many integers, and this is known to be in one-to-one correspondent to some geometry, smooth geometry called the Willy-Mathur geometry.
Excuse me.
Yes.
So in the free boson, it looks like so the only right mode.
Yeah, right or left,
Just only one.
only one. Yes.
Only one. Right or left.
Right or left.
I think
That's right.
Is there a simple explanation of why you get bosons in this example when you got fermions in the previous example?
Not that I know of. Free bosons and free fermions are the same thing. So, yeah, to this is not clear. Yeah. Okay, and you have some geometry like this. I don't really explain the detail, but now you have some arbitrary curve in R4, not in R2, and over this R4 you have some circle V fiber, and this curve is actually encoding how this S1 shrinks. S1 is finite away from this curve, but as you approach this curve, this shrinks, and it shrinks in the right way so that the entire space-time is regular and horizonless. And this again can be thought of as horizonless geometry supported by flux. Although I didn't write it down, there is some flux that goes through this geometry, and this is supporting the non-trivial geometry. And as I said, there's one-to-one correspondence with the CFT states. And the dictionary roughly is like this. So you have this curve, which is parameterized by this f of lambda, and you can Fourier expand this f of lambda, and then the excitation number of each Fourier mode is the number nk on the CFT side. So that's the dictionary. And you can even quantize the fluctuation of this curve in gravity, and you can find that the entropy is square root of n1 and 5, and this is actually the same as what you expect from the CFT. This was done by these people, so this is nice. So in this case, in the right, yes, yes.
Just only one closed curve is allowed, or you can have many disconnected?
At the supergravity level, there's nothing wrong with considering multiple strings, as you said. But actually, such configurations do not correspond to states in the CFT. Only one single string is in one-to-one correspondence with the state of free bosons. The reason is that so this CFT is supposed to describe a Higgs branch of the D1, D5 system, and it should be just one thing. The whole system must be one thing, and there must be no decoupled sector. Yeah, but if you have two strings, then this can be actually separated away infinitely. So this is not a single coupled CFT. Yeah. Any other questions? Okay, you can consider the classical limit, just like we said we did before. So how is this naive single geometry recovered? So I said that there's the two-charge black hole which is singular, and that's recovered by taking the classical limit again. So classical limit is GS going to 0, LS going to 0, and the charges are going to infinity. But we have to fix this combination finite. And if you do that, so the radius of this typical radius of this geometry is given by this or this. And if you send if you take this limit, it's easy to see that this R is going to 0. So although at finite LS, GS, and 1, 2, this system has finite size, but as you take the classical limit, this just shrinks to the singular configuration that we have. Yes. Okay. To summarize, so there are some examples of black hole microstates that are represented by microstate geometries. And in such examples, naive singular black hole solutions are replaced by bubbling geometries, geometries with non-trivial cycles with finite spread. And the radius of this thing is Planck times n, the number of branes involved, to some power. For example, in the previous example, we had this thing, so we had like a 1/3 as the power. So as if the more branes you put, the larger the spreading is. And this is, as I said at the very beginning of this talk, this is against the standard intuition. You normally think that the more you put, the smaller, the more compact the thing becomes because of the stronger gravity, but that's not happening. Okay, part 3, the fuzzball conjecture and the microstate geometry program. But are there any questions about what I have said? Okay. So, okay, that was interesting, and maybe that can be true for general black holes. So maybe black hole microstates are some stringy configurations spreading over a wide distance. So maybe you have some mess here, stringy mess here, and the size of the thing is like Planck times the number of constituents to some power, such that it's actually the horizon scale. Then this is going to explain the microstructure of the black hole. Okay? Yeah, I'm talking about the size, and I'm not talking about whether this is describable in classical supergravity or not. And again, if this happens, this is the case, it goes against the standard intuition in gravity, which says that the more you have, the smaller the thing must be. And so the fuzzball conjecture by Mathur is some more concrete statement about this. So the conventional picture is of a black hole is this horizon and singularity in it, but if you include quantum gravity effects, normally you would think that quantum gravity effect is confined near the singularity, but maybe it's not true, and it's going to fill the entire space-time with scale r horizon. So black hole microstates, maybe quantum gravity or stringy fuzzballs, and there's no horizon, no singularity, and it spreads over the horizon scale. And what I mean by this no horizon, no singularity, when there is no gravity picture, is that there may be some singularities allowed in string theory, and if you want to compute what happens if you send in some particle, then the scattering process is unitary and computable. So if you have a horizon, then it just gets sucked by the horizon, and the process is not unitary. But even if you have some stringy source, like the source of a brain, you know what happens if you send in in an object, and you know that the scattering process is going to be unitary, and it's in principle computable. So that's what I mean by no horizon, no singularity structure for stringy configuration. Okay, supergravity fuzzballs. So I said that in general fuzzballs are stringy, but are some fuzzballs describable in supergravity? And here by Sugra, I mean all fields in the massless sector of string theory. So you have G mu nu, B mu nu, Dalton, and overall fields and fermions, and only the massless sector. That's what I mean by supergravity. And this is probably unlikely in general, because general fuzzballs, general microstates must involve all massive stringy modes. Like this. Well, actually this is not precise in the sense that this is not the massive massless string, but never mind. And massive string modes are not in supergravity, so it's not likely that general fuzzballs are supergravity states. But maybe there are some hope for supersymmetric or BPS states, because massive strings are going to break supersymmetry in general. So, for example, if you have some massless mode of the string, which is BPS, then that means that the charge carried by the string is equal to the mass of that string. But if you consider higher oscillations on that string, then it's going to just raise the energy but not the charge. So it's going to be non-BPS. So this may mean that if you consider only supersymmetric BPS states, then only massless modes are involved and are described in supergravity. And LLM and Luni-Mathur geometries are supporting evidence in some sense, although the horizon area vanished. So whether it's going to be true for finite horizon black holes is not clear, but it's certainly an encouraging piece of evidence. And you can also say that there is even a more explicit example which says that this is true. That's the MSW black hole. So this is the Malus-Energy-Witten black hole made of M5 grains. So you wrap calabial with some M5 grains, and you also put some waves on that. And this is a black hole in 4 dimensions, and you can actually reproduce the entropy of that black hole by considering the traveling waves on this M5 grain. And traveling waves on the M5 grains is a brain probe picture. But if you turn on gravity, then the traveling wave M5 grain is going to be some back-reacted geometry, and I don't see why you have to incorporate non-supergravity modes when you do that. So maybe this is saying that this is really true, at least in 11 dimensions, where you can describe this MSW. properly. Okay, anyway, this is some supporting, encouraging evidence. So maybe in supergravity, for supersymmetric black holes, microstates are in supergravity. But you may say that are supersymmetric states of any use? Well, of course. The first thing is that it's more tractable. You don't hope to be able to solve the general supergravity equation for non-supersymmetric case because the equations involved are second order. But if you consider supersymmetric ones, the involved equations are first order, so it's more tractable, so that's better. And also, it can tell us about the mechanism. So what we want to know is the mechanism for the horizon-sized structure, and it is known that this mechanism can be seen in the supersymmetric cases as fluxes supporting the structure, as I will explain later. And also, you can also probably say that basic string theory objects are always locally supersymmetric. So we know supersymmetry breaking configurations in string theory, like D8, D8 bar, but locally things are supersymmetric. I don't know of any intrinsic stringy object which is intrinsically non-supersymmetric. So maybe by studying such things, we can study the dynamics locally, and combining such pieces, you can even understand non-supersymmetric cases. Okay? Okay, some more words. And you may wonder if there's absolutely no hope for non-supersymmetric states. It's not so, you don't have to lose all the hope. In the first place, if something is described in supergravity or not is a tricky question, and I don't know the answer. For example, you say that higher stringy oscillators are not described in supergravity, so massive strings are not in supergravity, but if the string gets macroscopic, then you can. For example, there's this Polyakov macroscopic string rotating in ADS5 like this. So this is a single string going around spinning in ADS5, and this is a huge solution, and this certainly back reacts. And why is it not described in supergravity? So it is described in supergravity. So if the string gets macroscopic, then it's somehow described in supergravity, even though it's a massive string. So maybe for the classicality of a configuration, it's not whether it is the large number of quanta involved that is important. So I don't know the final answer to this. So anyway, all I wanted to say here is that whether something is described in supergravity or not is a tricky question, and you don't really know the answer. So you can maybe remain hopeful. And also, the effect of massive modes could be captured in the massless sector. So you have integrated out all the massive modes, and you're left with the massless sector. But and you think that, okay, because you have just lost all the Hilbert space associated with the massive modes, but are they really all gone? Aren't they somehow captured by the massless modes? So at least if you include all orders in alpha prime expansion, then it seems to me that the structure of the Hilbert space of the massive sector must be somehow captured by the massless sector. I don't know if this is going to be captured in any sense by perturbative expansion, but anyway, this is also some thought that may say that actually there's some hope for non-supersymmetric states. Okay, and the last comment is that some non-supersymmetric microstates are already known, so it's interesting that there are such things, and maybe you can hope to generalize such solutions. Okay, I said many things. Many comments. Okay, some more words, caveats. So as I said, very very general states have large curvature, and this is what I already said. And there were some questions about this, so I'm not going to repeat this. Okay. Okay, so there are some things to be careful about. And there's other thing, non-geometries. So geometric spacetimes are not the most generic spacetimes in string theory. String theory is a theory of strings, and in general, the background that's described by strings are not geometric. And there are non-geometric microstates possible, and we have written down some explicit examples recently. And for example, you can have some exotic non-geometric supertube, and as you go around this curve, you may go to some different spacetime, because string theory says that two different backgrounds related by duality are the same thing and to be identified. So it's possible that you can have some very non-trivial configuration, and as you go around this guy, you go to a different space-time, but it's related to the original one by U-duality. So this is a fine, well-defined solution of of string theory. So this is something you have to keep in mind. And if you want to treat this kind of thing, probably then you have to extend the framework to probably double field theory or exceptional field theory that have been actively studied these days. Okay, but I'm not going to talk about this in these lectures. Okay, so the microstate geometry program is asking what portion of the black hole entropy of supersymmetric black holes is accounted for by smooth, horizonless solutions of classical supergravity. So this is the version of the microstate geometry program that I want to talk about here. The answer may turn out to be 0 or 1. Either way, it's interesting. And this is my definition here in these talks. And some other people want to consider microstates for non-supersymmetric ones as well. But here I only focus on these. And final comment, bottom up versus top down. So there are some arguments about structure near the horizon. For example, Malthur in 09 gave a proof saying that some one deviation from the flat space is necessary for Hawking radiation to carry information about what has fallen into the black hole based on quantum information. So this is saying that if there is a consistent quantum theory of black hole, then this flat space approximation of the near horizon geometry should be somehow be changed by an order 1 amount. And there's also the fireable arguments or arguments based on quantum information saying that there must be structures near the horizon. And in some sense, these arguments are bottom up in the sense that this applies to any quantum theory, quantum gravity. But this doesn't explain the mechanism why there should be some structure near the horizon. There should be some mechanism to support the structure. On the other hand, this microstate geometry program is said to be the top-down approach, and this explains why there should be finite size structure. And this is because you have some topology, non-trivial topology supported by flux. So these are like two complementary approaches. I'm not saying that the bottom-up approach is bad because it can explain the size. It's just the feature of the approach. So you have to work together to get a better picture of the black hole. And this is a very nice point to stop because this is. Okay, are there questions or comments?
Regarding the slide before, okay, why the answer should be 0 or 1? I mean, some partial. Or
Yeah, it can be 1/2 if you like.
okay, not from 0. Okay.
Okay, this is the most interesting case. This is the least interesting.
Okay, but okay. Also, partial result. Okay. I was convinced that you have an argument to say or total or nothing, but no.
No, well, but normally the entropy is going to be some power of n, and the power is important.
Okay.
And when the power is right, then the
Ah,
answer
you
is
say one, otherwise zero. I see.
Yeah.
Okay.
About this scaling relation of the radius with the n,
Yes.
has people tried to interpret this as some kind of UVIR mixing relation?
Oh, no, I don't know. How is there such an argument?
No, it seems to me so. I mean, because if you put things to, as you said, if you have more things put together, normally the attraction will try to put things together
Right,
and
right.
decrease the size. But instead of expansion, this is very much what happened in non-commutative geometry.
What happens in what?
Non-commutative geometry. I mean, this you expect to decrease in size, but instead you expand in size.
Right.
Yeah. So in that case, it's due to some RUE mixing. So this is gravitational. I don't know if people would try to think about this in terms of some gravitational RUE mixing. Yeah. Okay. Another question is how does the other quantity of the black hole scale with n? For example, like the mass or the charge. The charge is fixed.
Yeah.
What about the
Charges are fixed.
What about the mass? Do you know?
Well, it's also fixed. They are.
So it doesn't stay with n. It doesn't scale with n at all.
Well, we have to scale it appropriately.
Yeah. I mean, the reason I ask this is just because n is not something you can see from the classical black hole. It's sometimes it's a microstate already. So if you have some relation just of the black hole, then you can eliminate n and then try to see. I mean, to answer to have this picture of RUE mixing, I think you need to do this.
Okay. But the charge and mass are fixed parameters, and you don't really care about the.
You don't scale with n.
No, it's. Well,
The charge in some sense is scale with n.
it does scale, but
Yeah.
it's not like it's a. It's not like a result of the computation. You know how the charge scales with n.
Yeah, I just
begin
want to
with.
know. I mean, I don't know whether it's a computation or not, just the result.
But in string theory, you know how the charge scales with n, right?
Yeah, you can tell me. So what's the relation?
It's not like the result of such program.
No, I don't need it to be result of any program. I just want to know the formula, the index, alpha.
I probably misunderstand your question. But Q is like GS times
Yes,
n,
sir.
right?
Huh?
Q is like the charge is Q GS
I was
times
asking the
n.
mass. The mass.
Mass is also, in the previous case, Q and M are the same. And
Ah.
I don't know what kind
Okay.
of non-external black holes.
So it's just proportional to n.
Hmm?
Proportional to n.
I'm sorry? Proportional to n.
Yeah.
Yeah?
Okay.
Yeah, that's the simplest case.
Yeah.
Yeah, you can consider arbitrary non-extremality, but isn't that up to you?
No, I'm not asking a question. Up to you how to answer.
Well, I think I don't understand the question.
I think I understand the answer.
Okay.